Assalamu alaikum friends. Today our topic of discussion is shear force and bending moment diagram with the help of problem. Here we see that this is the simple problem consists of a beam along with two reaction forces at point C and at point A that is acting upward along with the 2 point load that is 400 pound and 900 pound acting downward along with the 60 pound feet that is uniformly distributed load through the entire length. In order to find out the shear force diagram, we have to find out the reaction force first, that is at point A and at point C. So for that, in order to find out the moment, the reaction at point A, that is RA. So we found we have to take the moment at point C, and we have to consider the clockwise movement as positive. For that, we have to first of all we have to find out that this uniformly distributed load is converted into point load as well as mention their point of application. So when we multiply 60 into 18, we got that is 1080. That is the point load of distributed load that acts at the middle of the beam. Now we have taken the moment at point C. So for that we multiply the force up to a distance that is 400 into 6, that is 900 into 8, and that is the reaction force at point A, that is RA into 12. So we got, when we simplify this equation, we got the value of Ra, it is 670 pound. Now in order to find out the reaction at point C, we have to take the summation of all vertical forces, that is the equilibrium condition. So we got the value of Rc 900 plus 400 plus 1080 minus 670. We got the value of Rc, that is 1710. Now we have to find out the shear force at different points. So for Ra, that is the shear force, that is the reaction force, its value is 670. At point B, that is at this point, that is this point. So for that we have to sum up, that is the uniformly distributed load. We have to multiply 4 into 60. We got the value of 240. So this uniformly distributed load is acting downward and this reaction force is acting upward. So we have to sum up these value. We got the value of 430. So again we have 900 pound that acts downward. Again we have to subtract that is acting downward. So we have taken this downward forces as negative. So when we sum up these two value, that is 430 minus 900, so we got the value of minus 470. At point C, we do the similar process, that is minus 470, that is at point B. We have to sum up with the uniformly distributed load. So that acts at from the point B to point C, that is 6 pound, 60 pound into 8. So it gives us the value of minus 950, that is at this point, but here again we have the reaction force at point C. So we have to add this 1710 that is acting upward. So we got the value of 760 again at point D. So we have to sum up all these, that is 760 minus, that is the distributed load. So we got the value of 400 again at point D. So we have a point load that acts downward at point D. So when we sum up these two values, we got the value of zero shear force, that is at point D. In order to find out the shear force diagram, first of all we have to draw the beam along with the point load, distributed load, as well as the reaction force with direction. So we draw the perpendicular line through all these points. So for that, for this point, that is the reaction at point A that acts upward. So we have drawn the line that is at the direction of this force. So that is 670 up to scale. At point B, that is the distributed load, only distributed load. So we have to come down because at this point the uniformly distributed load acts downward and this reaction force is acting upward. So we have to sum up these two values. We got the positive value, that is 430. Again we have 900. So due to 900 found the value of this, when we sum up these two values as we have done earlier. So we got the value of minus 470. That is at the, that is downward from this horizontal line. Again, at this point, we calculated earlier that at this point the value of shear force is minus 950. At this point, that is negative. So again, we have this shear forces, that is the reaction at point C. So when we solve these two value, we got the value of 740, that we goes upward, because this is the point load. For point load, we have to go straight. For distributed load, we have to draw a line that is inclined to the entire length. So again we have a distributed load. So due to this distributed load that acts downward, so we got the value of 400. Again, this is 400, and this is this is positive value, and this is negative value. So when we sum these two value, we got the value of 0 shear force at point D. In order to find out the bending moment diagram, first of all we have to apply the area method. For that, we have to calculate the area of all these figures, that is this point, this area and this area. So the above area is taken as positive, but then the downward area is taken as negative. So we have to calculate all this area that consists of triangle and rectangle. So this is a1, this is a2, this is a3. So we have to calculate. So a1 is consisting of two area, that is triangle and rectangle. So we have to multiply. So we have to take so we have to calculate this area, that is triangle and rectangle. So how we can calculate? So for that, how we can calculate the height of this point, the rectangle? So we have to subtract 430 from 670. We got the value of 240. So we have to multiply the length, that is 4. So plus 430, that is the value of this region. So from the shear force diagram, that is 430 multiplied by 4. So we got the area of rectangle. So at the result, we got the value of 2200. Again, we have to find out the area A2, as well as that is this area and this area. So the sum of area of the rectangle as well as the area of the triangle. So we got the value of minus 5680, that is acting downward. So we provided the sign convention negative. Similarly, we find out the A3 area, that is also a rectangle area and a triangle area. So when we do so we got the value of 3480. In order to find out the shear force diagram, we have to do the similar thing as we have done with the shear force diagram, that we have to draw the beam as well as uniformly distributed load, the point load, as well as the reaction force, and as well as the vertical line through each point, that where the load changes. So at point A, we have no moment at this point. So we have 0 at this point. Again, at this point, we have calculated the area of this region up to this region, that is 2200. Again, this slope is positively decreasing, because as we see that in the figure, that this is the positive area, but their slope is decreasing. So we draw the line that is positively decreasing their slope, because at this point the slope is maximum, but this point the slope is minimum. Again, for this region, we have the region that is negative area, but their slope is increasing, because negatively increasing. So we have to draw the line that is negatively, that comes down, that is negatively, and their slope is increasing as we go down, because at this region the slope is minimum, but when we goes downward, so their slope is increasing. Again, for this region, we have positive area, but their slope is decreasing. So we have to draw the line that is positively decreasing. So we goes down, that is positively, and their slope is decreasing gradually. Thanks for watching.